Hello, everybody. My name is Armin Iraji, and today I'm going to talk about the concept of functional multi-connectivity and introduce an approach to study through multi-way entanglement between network and voxel. Functional connectivity and interaction between brain entities commonly computed through the first level temporal coupling, for example, using peer correlation or mutual information between brain regions or brain network. However, this focus on the first level temporal coupling is likely missing important information about brain function because the brain is a densely interconnected system in which elements can communicate and interact with each other through more than one pathway, and different regions can be involved in different tasks at the same time. As such, we must move beyond typical approaches of estimating functional connectivity. We suggest the brain has a multi-connective functional architecture in which the interaction of an entity with the whole system must influence and being influenced by the interaction of other entities in the system. Here, we propose a framework to capture functional multi-connectivity, or FMC, by computing the relationship between system-wide functional connectivity of intrinsic connectivity networks, or ICNs. We calculate multi-way entanglement between intrinsic connectivity network and voxels. Entanglement refers to each brain network being heavily enmeshed with the activity of other networks. For this purpose, we estimate intrinsic connectivity network, or ICNs, using independent component analysis. fMRI data of each individual was first pre-processed, which include brain extraction, slice timing, motion correction, registration to MNI space, resampling, and spatial smoothing. Next, subject level and group level spatial principal component analyses were applied, and 100 principal components that account for maximum variance were selected for further analysis. Next, Infomax was used to estimate 100 maximally independent components. To ensure the stability and reliability of the independent component, Infomax was iterated 100 times, and the best components were selected using ICASO framework. The subject-specific independent component and associated time courses were then calculated using group information guided ICA, and 53 independent components were selected as ICNs based on their spatial and temporal properties. After calculating ICNs, the functional connectivity profile, or FCP, of each ICN estimated by calculating the Pearson correlation between the ICN time course and time course of every voxel. Functional connectivity profile encodes the network to voxel interaction representing system-wide functional connectivity of ICNs. Functional multi-connectivity, or FMC, is estimated as the amount that functional connectivity profile of each ICN can be explained using the functional connectivity profile of other intrinsic connectivity networks, which result in an asymmetric NI by NI matrix. We use a lasso to calculate the functional multi-connectivity, and the regularization parameter lambda was estimated using cross-validation. In the cross-validation, lambda equal to 0, which is equivalent to the least square, was also included. In other words, the minimum least square was considered as one of the potential solutions. In addition to functional multi-connectivity, or FMC, for comparison, we also calculate functional network connectivity, or FNC, as it is the current benchmark for studying functional connectivity using fMRI. functional network connectivity is a symmetric matrix, which means CIP is equal to CPI. After calculating FNC and FMC, we evaluate functional multi-connectivity in different ways. First, we evaluate if FNC reflect brain functional architecture. For this purpose, we apply a modularity detection on functional network connectivity and functional multi-connectivity separately. If functional multi-connectivity contains information about functional brain architecture, it should result in community or module that reflect brain functional architecture rather than random grouping of ICNs. We compare the FMC and FNC modules with functional domains. Each functional domain is a group of related ICNs. In our study, 53 ICN were categorized into 6 functional domains based on their prior knowledge, including anatomical and functional properties of ICNs. Functional domains are subcortical domain, somatomotor domain, visual domain, cognitive control domain, default mode domain, and cerebral domain. For functional multi-connectivity, 3 ICN were assigned to community different than their functional domain. These ICN are labeled by a square, and the color of a square represent their assigned module. For example, 2 ICN from cognitive control were assigned to the somatomotor domain, and 1 ICN from the default mode were assigned to cognitive domain. These 3 ICN show a disparity in functional network connectivity community detection analysis shown in circles. ICN from the default mode domain were assigned to subcortical domain, and those 2 from cognitive control were assigned to somatomotor domain. However, functional network connectivity modularity analysis assigned 4 additional cognitive control domain related ICNs to cerebral domain, even though we expect them to be assigned to a cortical domain. We also evaluate the power of the functional multi-connectivity to differentiate between 151 individuals with schizophrenia and 160 typical control individual. A linear SVM classifier was used for 3 scenarios, using functional network connectivity feature only, using functional multi-connectivity feature only, and using both FNC and FMC features. We also identify the most important feature for diagnosis using loss of feature selection procedures and a derivation of nested cross-validation. For feature selection was run for 1,000 mutually independent iterations. For each iteration, 90% of individuals were randomly selected, and tenfold cross-validation loss of feature selection approach was applied. Features selected in at least 90% of iterations were identified as significant predictor for diagnostic, and the average coefficient value across 1,000 iterations indicate their discriminatory power. The result of classification shows that functional multi-connectivity, shown in green, perform better than functional network connectivity, shows in red, based on different classification criteria, including accuracy, sensitivity, specificity, and many more. However, the highest diagnostic performance achieved when we combine functional multi-connectivity and functional network connectivity feature. The combination of FMC and FNC greatly outperform both classification using FNC or FNC feature alone. 6 functional connectivity pair and 5 functional multi-connectivity pair were identified as important features for differentiating schizophrenia and typical control individuals. The line and arrows respectively indicate functional network connectivity and functional multi-connectivity pair, which were identified as significant predictors for diagnostic. Hot and cold color represent positive and negative relationship between feature and diagnostic. Arrows direction indicate the entanglement direction. A to B indicate the amount that functional connectivity profile of A or FCP of A predict FCP of B. The thickness of lines and arrows indicate their discriminatory power. For FNC, subcortical domain is the most disrupted domain, while for FMC, functional multi-connectivity, alterations are distributed across several domains, including visual, somatomotor, and cognitive control. The results were similar for different threshold values. For instance, using a more flexible threshold of 50% instead of 90%, we still see subcortical domain as the most disrupted domain for FNC, and for functional multi-connectivity, alterations were distributed across several domains. We also observed significant correlation between a pair of functional multi-connectivity and positive and negative syndrome scale, PANSS cognitive score. This relation remains significant after correcting for age and gender. In conclusion, because the brain is highly interconnected system, interaction among brain regions and the influence of these interactions on the system as a whole are crucial to understand the brain function. While brain function is commonly studied using first-level interaction, for example, functional network connectivity, here we propose a framework to study high-level interaction and functional multi-connectivity, or FMC. FMC evaluate how functional connectivity of each network with the whole brain impact by the system-wide interaction of every other network. Moderately analysis suggests functional multi-connectivity compared to functional network connectivity can successfully identify functional community of the brain. Functional multi-connectivity has a higher discriminative power to differentiate schizophrenia and typical control, and they have a complementary information that together with FNC improves significantly the diagnostic power. Functional multi-connectivity identify subcortical, visual, somatomotor, and cognitive control domain are equally altered by schizophrenia, and all these domains have been reported to be altered in schizophrenia in previous study. Future work should incorporate time-varying properties and temporal delay in analysis. Thank you so much for your attention.